Welcome to the PowerPoint presentation on the modes of the rectangular waveguide. So before moving on to the modes, we will just have a small recap of the general points about transmission lines and waveguides. So we know that a transmission line is capable of transmitting signals from the lowest frequency till a particular frequency. So we can call it from 0 till some range. So because it passes frequencies from 0 till a particular range, a transmission line is said to act as a low pass filter. But when we talk about waveguides, the waveguides are capable of transmitting very high frequency values. So they start transmitting from a high frequency and it extends up to very high frequencies. And hence we say a waveguide acts as a high pass filter. So when we say the transmission line acts as a low pass filter and the waveguide as a high pass filter, we need to know certain parameters such as the cut-off frequency up to which the components are capable of transmitting the frequencies. Now using this cutoff frequency, we are going to find a mode of the waveguide which is called as a dominant mode. Why we find such modes we'll see at the end of this presentation, but the main motive of finding the cutoff frequency is to identify what is the dominant mode of the given waveguide. So we'll just start by saying a TM mode. So we know that a TM mode is in general represented as TM, M and N. So we know that a TM mode is represented as TM, M and N. This Mn is what represents the mode of our particular waveguide. And to just have a small recap, in TM mode, the component Hz is 0 and the existing field components are Ex, Ey, Hx, Hy and Ez. And when you observe the field equations, the four components Ex, Ey, Hx and Hy will be a function of Ez. Since Ez is present in the direction of wave travel, these four components will be a function of Ez and Hz is 0 for us. Now these are the four field equations of the TM mode. If you observe Ex, Hx, Ey and Hy, all of them contain a term E0 into some sine and cosine components, and this E0 term is nothing but it is a function of the electric field in the direction of propagation. So all these are functions of, it is the electric field term Ez. Now we need to distinguish between what are the non-propagating modes and what are propagating modes. So now we know that a TM mode is represented as, it is Tm and the subscript we have M into N. Now we're going to substitute various values for M and N and we will see what happens to the four field equations. So first let us take M equal to 0, N equal to 0. When we substitute M to be 0 here, cos 0 becomes 1, but sin 0 becomes 0. So the total equation goes to 0. Again here, sin 0 becomes 0, so the total equation becomes 0. Here again, sin 0 becomes 0, so the total equation becomes 0. Once again here, when substituted N to be 0, sin 0 becomes 0. Hy also vanishes to be 0. And in Ez, again sin 0 becomes 0, so the total equation becomes 0. So when you substitute M to be 0, N to be 0, we can see that all the field components become totally 0. And such a mode is not possible. We call these modes to be non-propagating modes where none of the field components are present. Now let us take N alone to be 0. When you make such a substitution, once again, all the field components become 0. So M0 is also one of your non-propagating modes. Again, substitute M alone to be 0 and let N be any other number. When we make such a substitution also, all the field components vanish and therefore this is also one of the non-propagating modes. So therefore, if either one of the term in this M and N is 0 or if both M and N are 0, it comes under the non-propagating modes. So we should not at all have a 0 term, which means for any value of 0 in the above field equation, all the field components vanish. So I cannot have 0 means I'm going to start from the smallest value of m to be 1 and n to be 1. So when you substitute m to be 1 and n to be 1, we get certain field component values. So this is the smallest value of a propagating mode, which is your TM11 mode. So for any value m greater than or equal to 1 and n greater than or equal to 1, we can say it is propagating in nature. Are you clear? So when you substitute m to be 0 or n to be 0 or both terms to be 0, all the field components vanish and hence they come under the non-propagating modes. Whereas when we substitute any value of m and n, either 1 or greater than 1, the field components exist and hence these are called as the propagating modes. Now let us come to the diagram of the TM modes. I have taken one mode alone, it is TM21 mode. So this 2 represents the value of m, this 1 represents the value of n. 2, 1 represents, so let us take, this is your x direction, this is your y direction. I don't take z because in z my wave is propagating. So we are just analyzing the field components in the transverse directions which are x and y. So this means in the x direction there are 2 half sinusoids. So consider the x direction. This is my first half sinusoid. This is my second half sinusoid. So here m value is 2. Now take, this is your y direction. In the y direction, how many half sinusoids do we have? It is 1 half sinusoid. So that is why this mode is called as the TM21 mode. So this m represents the number of half sinusoids in your x direction. This one represents number of half sinusoids in your y direction. And half sinusoid is nothing but, I think we know about a half wave rectifier or something like that. So these are called to be half sinusoids. So this diagram has 3 half sinusoids. So if you observe this diagram, here there are 2 half sinusoids. In this direction there is 1 half sinusoid. So this is called to be a TM21 mode. Now let us compare this diagram. So there are 4 modes which are present here. This TM11, TM12, TM21 and TM31. So this 4 diagrams, they are actually simulated using a software and the field components are presented here. So let us observe how this 2-1 mode is represented in this simulation. So let us take this to be the x direction and this to be the y direction. So how many 2 half sinusoid variations are there? My first half sinusoid, my first variation, this is 0. This is my second half sinusoid. This is my 0. So how many variations occurs to go for a half sinusoid? So this is half sinusoid, the first variation, again half sinusoid, the second variation. So which means there are 2 variations in the x direction. Now come here. So this is a 0, a half sinusoid, again 0. So this we have only 1 half sinusoid and that is why this is called to be a TM21 mode. You can check the similarities in TM11, 12 and 31 modes also. But in our prescribed textbook, we are given the field component of only the TM21 mode. So let us try to analyze that particular mode alone. So just to make you clear, the 2 represents number of half sinusoid in the x direction, 1 represents number of half sinusoids in the y direction. Now going to the TE mode, it is again represented as TEMN, where M and N represents the modes. And for a TE mode, we know that the EZ component is 0 and all the field components EX, EY, HX and HY will be functions of headset. So once again, these are the four equations. It is Ex, Hx, Ey, Hy. All of them are functions of the H component in the direction of propagation. And once again, to study the non-propagating modes, so we're going to study, it is about a TE Mn mode. So substitute M to be 0, N to be 0. We can see that your Ex becomes 0 since we have sign 0. EY becomes 0 since we have sine 0. HX becomes 0 since we have sine 0. And HY also becomes 0 since we have sine 0. So if you substitute such values, once again all the transverse field components vanish to 0, and therefore this comes under your non-propagating modes. Now coming to propagating modes. So we will try to substitute m to be 0 and n to be 1. Just a moment. We will try to substitute m to be 0 and n to be 1. So when you make such a substitution, we can see that not all the field components vanish to 0. Definitely few components are present. Similarly, when one term is kept as such, the other term is 0 also, the field components are present. And for any value m and n greater than or equal to 1, the field components are present. So all these comes under propagating modes. So this is a field configuration diagram of the TE modes. So as given in the diagram, this represents, the vertical axis represents the y direction. This horizontal axis represents your x direction. So we're going to start from the basic mode, which is TE10. So 1 represents 1/2 sinusoid in your x direction. 0 represents, if you see in this, there is no variation at all. It is totally blue. Blue represents there is no variation of field components, and red represents the presence of a sinusoidal component of maximum intensity. So here it is 1 component in your x direction and 0 component in your y direction. Now TE20. So there are 2/2 sinusoidal variations here and 0 sinusoidal variations in your x direction. So this again becomes 0. TE01. So 01 means in your x direction, this is your x direction, there is no field components at all. And the y direction, the vertical direction, there is 1/2 sinusoidal variation. So this is called to be a TE01 mode. Now talking about dominant mode, a dominant mode is taken from the propagating modes of the TE and TM waves. So the modes with the lowest cutoff frequency is what is called to be the dominant mode. So if we saw the basic propagating mode in TM was TM11, that is where few field components were present and not all field components went to 0. Similarly in TE mode we had TE01 or TE10 mode. So these two are called to be the dominant modes for a TE wave. So therefore for a TM mode, TM11 is the dominant mode, and for a TE mode, either TE01 or TE10 is called as the dominant mode. This can also be verified by substituting in the cutoff frequency formula. So this is a formula for cutoff frequency. This has to be known by us. So V is nothing but 1 by root of mu epsilon. This is nothing but the velocity of light. So I think this will be around 3 into 10 to the power of 8. And M is the mode. So here 1 means M is 1, N is 1. A and B represents the values of the waveguides. So here we have taken A to be 2.5 and B to be 1 centimeter. Now by substituting 1 and 1, this cutoff frequency we will be getting some value. Let it be for example 4. If I substitute, let this be 1, let this be 2, I am getting the cutoff frequency to be 6. So on comparing the cutoff frequencies of various modes, we can observe that TM11 has the lowest cutoff frequency, and hence this is called as the fundamental mode or the dominant mode of TM. And similarly for TE, we can try substituting these values, and when measurement is being made, this mode is said to have the lowest cutoff frequency. Hence 0, 1 and 1, 0 are said to be the dominant modes of the TE wave. Fine. Now we need to see what are degenerate modes. So degenerate modes are modes which have the same cutoff frequencies. For example, we take TM11 and TE11. So this is just a sample graph. So for both TE11 and TM11, the cutoff frequency lies exactly somewhere between 6 and 9 GHz. So TE11 and TM11 are called as degenerate modes. Similarly, TE21, TM21 and TM31 and TE31 are said to be degenerate modes because they have the same cutoff frequencies. Now why to study about dominant modes? When I make a waveguide To propagate waves in the dominant mode, three main advantages are observed. One is it is capable of transmitting very large frequencies in the same mode. The second advantage, we can have less distortion, and the third advantage, it is most efficient. So the main use of designing any device is that I need the total energy from the source to reach your destination. So by designing a waveguide to operate in the dominant mode, we can ensure that if I supply 100% of energy at my source side, I can achieve at least up to 99% of the same energy at the receiver side. That is why we study about dominant mode and we try to propagate the wave through the waveguide in the dominant mode. Thank you.